Hi, it's great to be here with all of you. I was here quite some years ago, and it was wonderful for me. I got lots of good feedback, so I hope to get that again, elicit that today as well. This is more about our concerns as we're developing an online algorithm. This is in mobile health. So what's our dream? Our dream is to develop algorithms that allow us the mobile device to continually learn as a person uses that device. And in particular, we're focused on behavioral type strategies that a person can use to help them be more active, to maintain their weight, to manage their depression, and so on. So we want to provide sufficient short-term reinforcement to the user of the mobile device so that they can make a good trade-off of their future happiness with their long-term goals. And the ideal mobile health intervention will engage you when you need it, and you can benefit from that engagement, and won't intrude when you won't benefit. And this is the big conundrum, I think, in mobile health, is bothering people too much. Also, it will adjust. It will continually learn. That is, it will adjust to unanticipated life events. So I'm going to talk about a particular sequence of studies that we're involved with. The goal is to have a mobile activity coach. These are people who had a cardiac disease. They had a surgery, some sort of severe cardiac event. And then they went through cardiac rehabilitation. This is usually 2 to 3 months of very closely supervised exercise with an enormous amount of support in a very supportive environment. And then they come out of that environment, and they're supposed to try and maintain their activity level in the following time. And unfortunately, for the most part, within a year after the cardiac event, people have returned to the same behaviors that got them into this trouble before. And there's multiple issues here. It's not only activity, it's stress management and healthy eating, but we're going to focus on activity for this talk. We already ran the first study, which I call a micro-randomized study. You'll see what I mean shortly. That was with 37 sedentary individuals because we're working on the software on the app. And now we're planning the 90-day study, and this will involve people who have just graduated from cardiac rehabilitation. And this 90-day study, we're going to pilot an online learning algorithm to personalize. And you'll see what I'm talking about as we go through. Okay, I just wanted to describe the first study. So the first study was with sedentary people. There were only 37 people. And it was a 42-day study. And there was a variety of experimentation that was going on. So it's very much like, getting on the web and having Google experiment on with ads on you. So here, we were collecting a variety of information, both real-time at different scales, daily, real-time. And then we would detect whether or not you were available for an intervention. You couldn't be driving. And if you were, we would randomize you. And this randomization it occurred at 5 times a day. And we set the probabilities so 3/5 of the time you'd get an intervention. And this intervention was a tailored prompt. It was tailored to where you were at that time, the weather outside, the day of the week, time of day. And so the content of that activity suggestion, this tailored prompt, was specified by where you were and so on. It was the tailoring. So you were randomized to either get that tailored activity suggestion or not, with a probability 3/5. And this occurred repeatedly over every day for 42 days, 5 times a day. And there was also randomizations going on in the evening as well. And we were looking at different kinds of activity. In particular, we were interested in, if you get a prompt, this tailored activity suggestion, are you more likely to move in the subsequent 30 minutes versus not? And this was all in preparation for the second study, which will then be in preparation for the last year-long study. So the second study, this is what we're preparing for now. It's going to have a good bit of experimentation going on. The first is, we're going to consider the tailored activity suggestions, and you'll see why when I discuss the results of the first study. But these do occur at 1 of 5 possible user-determined times per day. And then also, we're also going to provide or randomize tailored anti-sedentary suggestions. Now, this is a little different. These randomizations don't occur at particular times per day. They occur whenever a user has been sedentary. Both of these top two require machine learning algorithms, online algorithms to do the randomization. And we're going to focus on the first, but the second is quite interesting, the kind of algorithm one might develop to do the real-time randomization. There's also other interventions that are being randomized in this study every morning, every evening, and then once a week. It's a 3-month study. Then, as is typical in mobile health interventions, there's a lot of other aspects to the mobile app. There's a personalized coach, daily step goals, but these are not being experimented with. Everyone is provided that content. We're going to focus on the first for this talk, how we're planning to conduct that randomization. That is the randomization of whether or not we provide a tailored activity suggestion. I want to mention these 5 possible times per day. These are times that were determined by looking at large amounts of data, users, and they were times at which you saw the greatest within-person variance in their activity level. These are all people with regular jobs, and you saw a lot of within-person variance in activity right before the morning commute, around midday, around mid-afternoon, around the evening commute, and then after dinner. So those are each user specifies those times, and those are the times at which they might get a suggestion. Okay, so the kind of data that'll come out of the version 2, the online data, is there's a wearable band the person has. This, of course, measures their step count, also their heart rate, and a pretty crude measure of sleep quality. Then, of course, there's a whole variety of sensors on each person's smartphone. We'll be using an iPhone in actually version 2, whereas we used an Android in version 1. And the iPhone we'll be able to extract some information from the iPhone. And then we'll have nightly self-report. And you'll see an example of how one can also, in addition to the nightly self-report, collect other types of information in an unobtrusive way shortly. So let's think about version 2. So we're planning version 2 right now. And what we want to do is we've already considered these activity suggestions, and I'll talk to you about the results from the first study in heart steps. But in this second study, we want to, during the study, alter the probability with which we're going to provide an activity suggestion versus not as the study progresses. And we want to do this in a way so that we provide those suggestions in the setting in which it's most helpful to the person. And this is a big issue. If you're familiar at all, if you've ever used a wearable device for activity, or you get pinged a lot, you get prompted a lot, and very, very rapidly people habituate to the prompts. We just ignore them, or we delete the app, get rid of the prompt altogether. So it's really important to only deliver these suggestions at times in settings in which they might be efficacious. Because when you deliver them when they're not efficacious or minimally efficacious, it makes for a disaster. Okay, so I just wanted to show you a little example. So as I mentioned, there's a personalized coach on the phone. This personalized coach is called Sam. And a little tailored suggestion, if it appears on your lock screen. And you can see this one was, I think it was in the morning on a work day. So it's just, why don't you just walk around the office. And when you get this notification, you can make it go away by pressing thumbs up or thumbs down. So this gives us an immediate feedback. It's not about whether you took a walk or you got steps, but whether or not you found it useful. And this can occur up to 5 times per day. So let's talk about some of the results from the first heart steps that are going to guide our thinking about the second one. So we had pre-specified, these are clinical trials, and clinical trials, they're randomized trials. You do pre-specify the primary analyses and some secondary analyses, and of course, and you have to pre-specify the primary outcome as well. And here, the primary outcome was the step count over the 30 minutes following a decision time, each of those 5 decision times per day. So it's the step count following that 30 minutes. And we pre-specified that, and we thought, of course, we hypothesized that if you got a suggestion, you'd be more likely to walk in the subsequent 30 minutes versus not. And we were also concerned about deteriorating effects because of habituation. And in fact, we were really fortunate. It turned out our hypothesis stood. It was a pretty strong effect. So here you see it written. The tailored activity suggestions compared to not bothering people. It initially increased an individual step count over the subsequent 30 minutes by about 271 steps. That's the beginning of the study. People in this study, in 30 minutes, they were getting like 300 to 500 steps prior to the study. So this is a big increase in number of steps. But by day 20, 3 weeks into the study, the increase was only 65 steps. So as the study went on, we hypothesized it's habituation. They just didn't even see the notification anymore. These are the results. In the first item is the results that we feel really confident about. We pre-specified those hypotheses, and indeed we saw them. And the second here is where we were planning for the next study. So I just say that appear to predict. So what are some of the aspects of the context that appear to predict the subsequent 30-minute step count? Remember, there's 5 times a day. At each time, you may or may not get a suggestion, and there's 30 minutes subsequent step count. So time in the study, I mentioned that already. The longer you've been in the study, the lower the effect. Number of messages sent in the past day. So the more messages you got, the less likely you were to respond on the subsequent. This makes sense. Some aspects of location as well. This is quite interesting. Variability in step count in the 60-minute window over the prior 70 days. So the 30 minutes before that time point and the 30 minutes after, if that was a highly variable time for you, you were more likely to respond to the subsequent activity suggestion. And then these other features, they didn't predict how responsive you were. They just in general predicted your activity level. So how active you were in the prior 30 minutes to that point in time, that was strongly correlated with how active you're going to be in the subsequent 30 minutes. Your total steps on the prior day, and the weather, the temperature outside. See, so all of these are important because they're the aspects of context plus some other aspects that we didn't measure in Heart Steps 1 that we're adding on to Heart Steps 2. These are all aspects of the context that we think, this might be a way to utilize to decide whether or not we send an activity message in the second Heart Steps. So what we're going to discuss here is the use of what's traditionally called a Bandit algorithm. And the idea here is that traditionally with a Bandit algorithm, the idea is to select treatments so as to maximize the sum of rewards over the time points. So our reward is how much the person stepped in the subsequent 30 minutes. That's following each of those 5 decision points per day. So we want to maximize that sum of steps, step counts. And we have a 12-week study. So traditionally, that's how you would design an algorithm. This is the goal. You want to maximize that. And okay, so one of the things Bandit does is it ignores the delayed effects of treatment. That is, the goal. The Bandit just focuses on the immediate impact of whether or not on your step count, of whether or not I provide you a tailored activity suggestion versus you're not provided tailored activity suggestion. It ignores any kind of increase in feelings of burden or an increase in habituation. So it could, in fact, it could be that if I took a breather, if I allowed these participants to take a breather in the middle of a 12-week study, I might get an overall higher sum of rewards than if they don't get a breather because they have a chance to dishabituate. But the Bandit ignores this. It ignores these delayed effects. And there's a good reason why I, as a developer of this algorithm, might be interested in that. And that's because Bandit algorithms, they learn much faster than algorithms that take into account delayed effects. It's just really hard to anticipate delayed effects. There's a lot of noise in that anticipation. So in effect, what's a Bandit doing for me? It's acting as a regularizer. So if you're used to, like in machine learning, we use all kinds of tuning parameters that regularize for us. The Bandit algorithm itself is a regularizer. What it's doing is it's trading the speed at which I can learn in which context it's best to provide an intervention with some bias that I might choose. I might accidentally provide an intervention when I shouldn't, or vice versa. And to the extent that I have less delayed effects, there's less bias, and I learn fast, and vice versa. So I'm paying that price. I'm trading speed of learning with bias. And I know that this is not a theoretical conference, but we really need some theoretical work on this topic of how the Bandit works as a regularizer. Okay, so I'm not sure. I think most people do a lot of supervised and unsupervised machine learning as opposed to decision making. So I wanted to provide a little bit of a review. Okay, so we initialize parameters at the beginning of the Bandit algorithm on an individual. I have initialized the parameters in the expected reward, the expected number of steps I will take in the subsequent 30 minutes. This expected reward is a function both of whether or not I get a suggestion, treatment, and it's my current context. At each time point, I input the current context, that's denoted by ST. The Bandit selects a treatment, and then we observe the algorithm inputs the reward, that is the subsequent 30-minute step count. Then the algorithm updates the expected reward, and then that's always a function of the treatment and the context features. And then using that updated expected reward, it chooses the next treatment at the next time. So it goes to the next time unit, observes the current context, and chooses the treatment using that updated reward. So at each point in time, in a sense, I predict how many step counts you're going to get if you get treatment versus not. I choose whether to give you treatment. I see how you responded. I go to the next time point. I predict how many the expected number of step counts if you get a treatment versus not in that context. I choose whether to treat. I get a reward, blah, blah, and go on and on and on. That's the way the Bandit algorithm goes. So it's that type of personalization within a person. So we're going to be using a linear Thompson sampling Bandit. And so when I say Thompson sampling, that's just an old term for using a Bayesian paradigm. And you'll see that shortly. So I'll explain why we're using a linear model as well. But the expected reward given context ST at time t and treatment AT at time t is just a linear combination of some features. And what the because this is a Bayesian paradigm, what you do is you have a prior distribution on the coefficients, the eta coefficients. You start off with that. Then you observe a context, select an action, get the reward. You update your posterior distribution of the weight of those features in the expected reward. We're going to have a Gaussian posterior distribution, so you get an updated mean, updated covariance matrix. Then this is a slightly different way of explaining what the Bandit does than one usually sees in the literature. I see the next set of features. Then I calculate the posterior probability that an action is better than no action. If that probability is, say, greater than 0.5, in the case of no action versus action, then I choose to provide a suggestion. Okay? So the posterior probability that an action is best, that's the probability with which I choose that action in the next round. So if you're a statistician and you think about this problem, you realize in your mind, man, this Bandit algorithm is just a sophisticated way to do randomization. It's a randomization protocol. It's sophisticated, where the randomization probabilities are being biased in a positive way towards the treatment decision, which appears to be doing best in that context. So I'm going to go through a number of challenges that we've been thinking about, mainly because of our experience with HeartSteps version 1. And I'll give you an explanation, and then I'll end with one idea in particular. So the first aspect of this is the data is really noisy. This is very noisy data. You're following one person over time. You see their current context. You give a treatment, and then you see how they respond, their 30-minute step count. And in a sense, although the context might be high dimensional, the data in a sense is sparse. It's just one person's time series. So what we're going to do is we're going to learn a low dimensional parameterization of the expected reward. This is another way to regularize. And that's what I stated on the prior slide. F is just features of current context and treatment. And then how will we use our pool data in order to deal with the fact that pool information in order to deal with the fact that we have noisy data in HeartSteps version 2 is that we take the data from version 1, we use that to form a prior of these weights for version 2. Now, we won't be able to use it for all of the features because some of the features weren't collected in version 1, but we can use it to some extent. And in addition, in HeartSteps version 2, we're building in a week of no treatment where we'll be able to update that prior. So at the beginning of the treatment period, when randomization starts to occur, when the Bandit really starts to work, we'll have an improved prior distribution on those eta parameters. So that prior is formed by pooling over individuals. But then once you form the prior, it's all within each person separately. The next issue, and this was hinted at when I discussed the results from HeartSteps version 1, this issue of non-stationarity. Over longer periods of time, you can imagine that the reward as a function of current context and whether or not they get a treatment may vary with time. And this is probably due to the fact that we cannot really sense the entire context. And it's even worse than that. We don't know what the relevant context is. So our science is not at the stage where we can say, oh, this is a latent process. I mean, we can try to do that, but we often don't know what we need to put in the context, much less know how to sense it. So one of the solutions that we're working on testing is to, instead of having a Gaussian prior distribution on the regression coefficients, the etas, we'll have a Gaussian process prior. So we allow the coefficients in the expected reward to vary with time, slowly with time. This does introduce an additional tuning parameter. So I'll just comment on that slightly. So the tuning parameter is this gamma, and if gamma is equal to 1, you return to a standard Gaussian prior. If gamma is equal to 0, which you would not want, then you can you're saying the only relevant data for making a decision is the data we're getting now, and I've not learned at all. So you have to decide how much what the size of gamma, it has to be tuned, and we do that with Heart Steps 1 data. Here's another issue that comes up, and this is slightly related to the last, and that is, and this is particular to these kinds of treatments, but I think in general with most behavioral type treatments, this occurs. And that is, there's very little, minimal poor or negative effects in the near time of providing a push, of delivering a treatment with a mobile device. There's almost no negative effect. In fact, it'll always look better to provide the treatment, provide the activity suggestion versus not. In the near time, it almost always looks better. The real problems are the delayed effects, the fact that you're burdening people, the fact that they habituate. That's where the real issues are. Yeah, remember, we chose this Bandit because we need to learn fast. Right? Okay, so what happens is, if you're not thoughtful, is the algorithm, and we can see this by looking at Heart Steps version 1, is the algorithm will falsely learn that you should always treat because it doesn't pay attention to delayed effects. It says, yeah, always treat, man. Yet there's probably better policies in terms of maximizing the total sum of rewards, such as, leave the person alone, and then they'll be less habituated in a week or two, and then they'll be more responsive than they would have been otherwise. So what are we going to do? Well, we're not going to just dump the Bandit. Instead, we're really acting like engineers here. We're going to use domain science to reduce the posterior mean for the treatment, providing an activity suggestion using something called proportional feedback control. In other words, our collaborators say, look, the most I can tolerate you bothering these people, penultimate most is 6 times over the last 24 hours, so beta's like 6. And then every time, if we have a period of 24 hours where we reach that maximum, we penalize the mean, the posterior mean for that, choosing an action. And this is classical proportional feedback control. It's like a last-ditch effort to save us. Okay, and here's another issue that's come up with in this study, and I think this is one that we all have to confront, particularly if you're a lover or of reinforcement learning, as I am. We need to take care of our collaborators. We need to be on our collaborators' side, and we can't put them in a situation where if our algorithm goes off into la-la land, the whole study goes down the tubes. This is not good. Because then you've spent an enormous amount of money and you have nothing to say. So what we're going to do is we're going to facilitate the variety for off-policy secondary analyses. And what do I mean by that? Is we're not going to allow the Bandit to say with total confidence, yes, in this context, you should always provide a suggestion. In this context, you should never provide a suggestion. We're not going to allow the Bandit to do that. We're going to, in fact, ensure that the no treatment selection probability always stays between 20% and 80%. So there's always going to be some fraction of times that you will not get a treatment. And that continued exploration will allow us to do off-policy analyses after the end of the study. And that way, even if our algorithm messes up, we'll still be able to recover. We can still do some good science in using the batch of data set. Let me see if there's something else. Oh, this is the other reason. This is also one reason at this time, while we're, you see point 2, do not pool data from different individuals to select each individual's treatment at each time. This is really disconcerting. I really do want to pool individuals' data. It's a way to get to learn faster, and people are not that dissimilar. They're similar in some ways and dissimilar in other ways. We would really like to pool in real time over people. The issue here is that the minute you do that, you do prevent a whole variety of off-policy secondary analyses. And we're working on how you might facilitate that in future, but at this time we're not. This is the reason why I put all the question marks, because we would really like to pool over people. Okay, so this is the last challenge I'm going to talk to you about, and this is that the context, either observed or unobserved, is likely highly complex. I mean, it's high dimensional, and the reward, the expected reward, is probably a complex function of the context. And one thing, and here I give you a particular user from HeartSteps version 1, and the height of the bar is the number of steps the individual took. There's a lot of places where there's no bars, because they didn't do anything. They just sat there. And then the green bars are right after an activity suggestion. The black bars are after no activity suggestion. But you can see it's highly variable. And if you see other graphs, it's a pretty complex pattern. Of course, you can hope to explain it by the context, particularly if you have a large amount of context features. One issue, of course, is that we don't have a large amount of data. So even though I would like to use deep learning, that's not going to be feasible here. So what are we going to do? We're going to use a very old trick that comes out of econometrics and statistics. And what it does is it induces orthogonality. And the way this orthogonality is going to be induced, you're going to see this shortly, is by centering the treatment AT by the probability with which you selected that treatment. You're going to see that on the next slide. So, okay, so it says accommodating expected reward that is complex function of the context features, that's ST, that's the vector of context, in a setting in which you have small amounts of noisy data. So I'm just going to talk about it in the case of binary treatment. So AT is 1 if you get an activity suggestion, 0 otherwise. In general, you'd want to allow multiple types of treatments. So what we're going to do is we're going to replace our usual linear model, which I have here. We're going to replace it by a model which doesn't involve the treatment, and then a part of the model that involves the centered treatment. That is the treatment indicator minus the probability of getting treatment. So lowercase a is 1 or 0, and the probability of choosing treatment is pi t. Pi t is the posterior probability that treatment is better than no treatment, right? In the Bayesian algorithm. And this is just, so what have I done? First of all, I've made the model much more general. I've allowed the expected reward to depend on time, non-stationary. Second of all, because the treatment is binary, you can. This is equivalent. Even if I put a linear model in right here, and maybe pi t is one of my features, these would be equivalent parameterizations. So the only thing this does is it extends it to make it non-stationary. What have I done? Again, I want to make another. So if you just go back to baby statistics where you took regression, so this would be like maybe first year grad school, you see these design matrices when you do linear regression. And what's happened here is part of the design matrix has this term, the treatment minus pi t. And the expected treatment, it's binary, is pi t. So this part of the design matrix is orthogonal to any kind of model that you might put here. What that does is, even if you misspecify this model, you can use a working model, whatever you want here. Even if you misspecify it, it will not bias the ability to estimate the weights. And the only thing that counts in terms of deciding whether or not to choose treatment are these weights. So I think I say that. The baseline function is unspecified. It might be nonlinear. It might be non-stationary. It might be arbitrarily complex. And again, this is the posterior probability that treatment is better than no treatment. Okay, I just say everything over again here. So again, I'm just considering the case for clarity of a binary treatment. Capital AT or lowercase a is just 1 or 0. And I'm replacing that linear model by the sum of two terms. The second term, its design matrix, is orthogonal to any kind of parameterization you might do for the first term. And this is a way to protect you. And then in the Thompson sampling update, this is the Bayesian update. I use some working model for this baseline function. We're going to use a linear model. It's okay. It doesn't matter if it's right or not. That's not relevant here. This is this doubly robust idea that you see, yeah. And it originated in econometrics and statistics quite some time ago. Okay, I wanted to show you a result of using this, because we're running all kinds of simulations to try and anticipate how this trial is going to run, because we have to ensure that the trial goes well. So here in this setting, the context S is just three-dimensional. One of the context variables actually is just taken from HeartSteps version 1. We just took it out. We took the time series from HeartSteps version 1. The true baseline function is nonlinear, but we're going to use a linear model nonetheless. We're going to ignore that. We're not going to do any feedback control. We're not going to use a Gaussian process prior, but we are going to ensure that the probability of no treatment is between 20% and 80%. And we're going to have this linear working, use this action centering idea. And so here in the first little slide, we have 450 decision points over the 90-day study. So you see the regret. So what's the regret? What's the definition of that? The regret is you look at the series, the step count, the sum of step counts under the best policy, subject to the fact that no treatment has to be given with probability between 0.2 and 0.8, versus the number of steps you would get under the policy you actually are implementing here. And you see that the Thompson sampling, standard Thompson sampling in red, high regret's bad. Standard Thompson sampling doesn't do well because it requires that you really capture the influence of the context on the expected reward. Whereas because we're using this idea from econometrics and statistics, classical statistics, we don't have to capture that complexity. I wanted to include this slide. I think it tells me something. It tells me one has to think carefully about this. Okay, so here we have 500 simulated users. So these dashed lines are the quartiles. So this is the 75th quartile for the action-centered Thompson sampler in regret, the 75th quartile across the 500 simulated users. And the red line is the 75th quartile for the standard. And if you can see the lower 25th percentile, it's pretty much flat. So across, what's that telling you? It's across the 500 simulated users, you're getting a whole variety of regret curves. Some users just don't respond as well. Other users do really well. There's enormous variability. And this argues, and this has been known, that the Bandit algorithm has been known to have these kinds of problems in clinical trials literature. And this is something we're going to have to deal with. We have to find a way to deal with this. But nonetheless, the idea of centering the actions in order to deal with the complexity of a baseline reward is useful, appears useful. Okay, I'm ending early, so I just want to summarize here. So if you're a statistician, when you think of the Bandit algorithm, you might, in the context of mobile health, you see it as one way to do randomization. And randomization is great because then we can get causal inferences. Another way to do randomization is to randomize based on forecasts or predictions. And at the beginning of this talk, I mentioned that the other place that we need to do randomization is we have to decide if you're sedentary, whether or not to deliver an anti-sedentary message. For that particular treatment, we are developing an algorithm which every time you're sedentary, it forecasts the number of remaining sedentary episodes for the day and spreads out the number of times that will provide a suggestion to you. So you need an online prediction which forecasts the number of remaining sedentary. And this particular forecast now that type of thing is occurring over and over again in mobile health studies that I'm involved in when you're using treatments. I'm just repeating myself here. Randomization is great because it helps us form causal inferences. We don't have to assume, if you use observational data, you just observe when people use treatments or not. There's always a lot of alternative explanations for any results you get. Another challenge that comes up in this setting, and it's pretty bad, is missing data. So we actually, as a team, had to spend an enormous amount of time coming up with protocols for how the online algorithm will process and deal with missing data. Some of that missing data is actually a feature. It indicates the person is becoming overburdened or habituated. Other missing data is just due to technology. And in each case, we need to decide, are we going to use it as a feature, or are we going to somehow impute a value there in its place? The collaborators, Christian may be in the audience somewhere. He's the postdoc who's really involved in this. Ambush Tiwari, a computer scientist, and then Peja, he's a human-computer interaction guy. If you have any questions, please email me. Thanks.
All right, we have some time for a couple questions.
Obviously, there's a lot of issues with clinical trials.
Uh-huh.
Some of those talked about earlier. Some of the challenges you highlighted here are perhaps more specific to behavioral and health interventions, like the law.
Right.
Do you think of the biggest general methodological problems trying to shift clinical trial, general way of doing clinical trials from more of a frequency paradigm to more evolution?
Actually, this is we are using a frequentist paradigm here because we're only pooling over people prior to the randomizations. So at the end of the study, conditional on baseline data, we will be able to use frequentist statistics. And the reason why we're doing that is to protect our collaborators in case our algorithm is not so hot. So the real, in my opinion, the real challenge is that we would really like to pool over people during the conduct of the trial. Now, this is non-trivial because you don't recruit everyone at once. People trickle into these trials, and if you've ever been involved in clinical trials, there's a grotesque cohort effect. That is, people who come into the trial early tend to be very different from people who come into the trial later. So this pooling over individuals is not so simple. It's not like it's just a way to improve precision. There's going to be some real thought here because of the cohort effects that occur in clinical trials. But I'm going to ignore that. I do think there's a way for us to, there's something called design effects in the classical statistics, where you adjust standard errors due to dependencies between individuals. So you can use classical frequentist methods, but you have to adjust the standard errors. And I think we can develop that in this case. It's just that, and that could be used after the study, and thus would allow us to pool over individuals during the conduct of the study. So I actually think, I feel very hopeful about all of this. I'm having people, and I think us as, in this field, in the field of mobile health and behavioral science, we're getting, of course, using a language that people resonates with is really important, as you know, just as I do. But we're getting a lot of interest and desire. We now have many, many of these micro-randomized trials in the field.
We have time for one more question.
So great talk, very exciting. Looking forward to seeing the results. Maybe you mentioned it or I missed it, but how you're folding in the user's response, the thumbs up or thumbs down. When I drive on the commute, every time I hit the traffic on 120, my Apple Watch says, "Oh, now's the time to stand up." Like, there's some way to feedback this.
Yeah, okay. I actually kind of lied to y'all. There's this whole issue in mobile health called availability. And so we don't randomize at each of those 5 times. First, we sense whether or not you're available for randomization. So if you're currently driving, we don't even randomize you. So that's really makes for very interesting data analytics, okay? Because sometimes if you're currently walking with this particular study, we don't randomize you. Of course, you may be currently walking because you really like the suggestions in the past and you're using them. So there's really, there's a loop here, a feedback loop going on. And I just left that out, but that's not RL was meant for that type of a setting. So we're okay, but definitely we use sensors. If you're driving, we try to sense if we know a priori that it would be intrusive or unethical to ping you at a particular time, we don't ping you then.
All right, let's thank Susan.